All right. I will solve a number of problems that will help you with homework. And then if you have any questions, you can ask me. Is that right? Is that okay? All right.
Yes, ma'am.
Okay, thank you. Thank you, Cody. All right, so let me go to the homework first of all. Let me see. I don't have it here, but I don't believe I have it here. But in any case, oh no, it is here. All right, sorry. That's not even. I don't have the homework, but I will more or less give you something similar. It's not exactly the homework, but it's going to be something that it will help you. In any case, first of all, let's talk about different types of transmission lines, ideal transmission rights, rather, or ideal transmission line, say sections, because that you're gonna use this for the homework. Okay, let me move that here. All right, so first of all is a quarter wave transmission line. All right, so let's take one line here. And then take this one. Okay, now let's assume that this has a characteristic impedance Z1. And then here we have a load that connects to it. And this load is ZL. And then this is lambda over 4. Right? And we want to find the input impedance here. Z input. Oops, not normalized. That we use it for. Okay. So we know from ideal transmission lines that Z input for any length of line. Let's assume that this length is L equals lambda over 4 for now. Okay, it's Z1. And then is ZL plus J Z1 tangent beta L. And then Z1 plus J ZL tangent beta L, where beta is what is propagation constant, wave or wave number or propagation constant. For the transmission line. And beta equals 2 pi over lambda, where lambda is the wavelength. Okay, so one moment. Okay, then now lambda L here from the transmission line, L equals lambda over 4. So beta L equals 2 pi lambda times lambda over 4. So it's pi over 2. Okay. Then this one becomes Z input, Z1, and then becomes ZL plus J, Z1, tangent. Yes? 1 second. Come in. I'm on office hours. Close the door. Yeah. And then here we have Z1 plus J, ZL, tangent pi over 2. How much is tangent pi over 2? Do you remember? Tangent pi over 2, which is sine pi over 2 over cosine pi over 2. Sine pi over 2 is 1, cosine pi over 2 is 0. So it's infinity. Okay, that's 2. So let's now observe 2. Tangent pi over 2 goes to infinity, which means from 2, from the numerator of 2, what do we find? That JZ1 tangent pi over 2 is much larger than ZL. And then also from the denominator of 2, what do we find? That JZL tangent pi over 2 is much larger than Z1, which means that 2, I can rewrite 2, and it's going to be Z input equals Z1. But then in the numerator, since the second term is much larger than the first, I can ignore the first term. All right, I can assume that this is very small. I can assume that this is very small compared to the other one. So I have J Z1 tangent pi over 2 divided by J ZL tangent pi over 2. And then I cancel that as a common term. And then what I have is that Z input equals Z1 squared divided by ZL. Okay. So now I have, if I can find out, for example, how much Z input is going to be, because let's assume that ZL equal 50 plus J 50, for example, and Z1, it's in fact, let me change this one, make that 100, and assume that Z1, so we assume, all right, yeah, Z1 is 50, and these are ohms. In this case, Z input will be 50 divided by 100 plus J50, okay, which in fact and that's going to be in ohms, but I don't show it here. So in fact, I can divide by 50, both numerator and denominator becomes 50 divided by 2 plus j. And then what do I do to be able to find the input? I multiply numerator and denominator by the complex conjugate of the denominator. So I do 50, 2 minus j, and then I have 2 plus j, 2 minus j, and that makes it 100 minus j50. In the denominator, I have 4 plus 1. So then that gives 100 minus j50 divided by 5, which then gives me that, and that is in ohms. Which then gives me the Z input is going to be 20 minus J10, and that's in ohms. Let me see, one more. Okay. Any questions on this? All right. If you don't have any questions, then I'll solve another problem, which is going to also help you. So that's problem number 1. Okay, quarter wave transmission line. All right. 1 second. Let me make this a little smaller. All right, so now let me do a problem where we have a stub and to see how I would solve this. So let's say types of ideal transmission line sections. Okay, B is ideal transmission line. So it's a shunt stub a transmission line. So we'll take this one. Okay. And we'll put this, and then here. Then here we have a stub. assume it's a short. Okay. And let's assume that this, well, is 0 and that is 0. Let's assume that this length is D. And okay, this is A prime, A prime. This is B prime. And here we want to find the input, right? We want to find the input impedance at A prime. So how we're going to do that is the following. Let's assume that this also distance is L. Okay. So find the input. All right. All right. So let's assume that let me use a different color. I'm looking towards the line here, and I'm calling this input impedance Z in at A prime. And let's assume that this is for the transmission line, all right? So I'm calling it this. And then, so this is without, I'm in front of the stub, obviously. I mean, I don't see the stub as I'm looking towards the end of the line, the stub is behind me. And then I look at the input impedance here, maybe this one, inside the stub, like this, and I call that this Z stub, all right, at A prime. Okay. If I were able to find Z input at A prime and Z stub in the beginning of the stub at A prime, then this circuit looks like this. So figure 1. So circuit in figure 1 then becomes okay, this is A and A prime. And then this is the input at A prime. All right. And this one is Z stub at A prime. All right, so let's assume that this is 1, and there are 2 impedances in parallel. Now, I don't necessarily want to combine impedances in parallel. Whenever we have something in parallel, we change it into an admittance form. So practically, I can then say, now I know that Z input at A prime is the inverse of an admittance at A prime. All right, and also Z stub at A prime is a 1 over and at the admittance of the stub at A prime. When I do that and I have two admittances, then figure 2 changes into something that involves admittances. So in this case, I have and this one is the admittance of the section of the line that terminates at R sub L. That's admittance. And this is the admittance of the stub. Okay. Here. And here. In that case, how much is the total admittance at A prime? The input at total at A prime, therefore is the sum of the two admittances. That's what we do when two admittances are in parallel. So it's this plus this one. Okay. All right, now having said that, we can go back here to find Z input at AA prime, ZS at AA prime, and from there go the admittances and then so on. So let me going now, right, okay. Let me now go here and say step 1. Find the impedance, first of all, at AA prime. Okay, from what we just said before, this is going to be Z0 and then I will have RL plus J Z naught tangent beta L, and then Z naught plus J RL tangent beta L. All right, so now let's assume that L here is lambda over 2. All right. In this case, we have L equals lambda over 2. And from there, we have tangent beta L to be equal to tangent 2 pi over lambda times lambda over 2. And therefore, it becomes tangent of pi, which in fact is sine pi cosine pi. How much is that? 0. So then we have, for this case, we have that Z input at A prime equals Z naught RL over Z naught, which in fact makes Z input at A prime to be RL. Okay. And RL, we have not given it here. Let's assume that RL is 100 ohms. Okay, so here we found that Z input is 100 ohms, which in fact gives us that Y input at A prime equals 1/100, which is immense. All right, which makes it 0.01 Siemens. All right, now let's try to find Z sub S A prime. It's the same thing. It's a line. If you think the stub is a transmission line with characteristic impedance Z0, which has a short at the end. So now what that means, so step 2, the stub, the shunt stub, looks like this. Let me see what's cut by purple for it. So is a section of a line. That's the stub. That is shorted at the end. In our case. All right. And that is distance D, that is Z naught. And here this is A prime. And this is here the input impedance, Z input, Z stub rather. According, using the same formula as before, becomes Z naught. The load here is 0 because it's short. All right, so it's going to be RL prime plus J Z naught tangent beta D over Z naught plus J RL prime tangent beta D. RL prime is 0, so that gives us Z sub S at A prime. Let me see how I have it. Yes, I have Z sub S in the denominator somewhere. It's here. Is Z naught J Z naught tangent beta D. And then in the denominator is Z naught because the RL prime goes to 0. So it's this one, which means from here that Z sub S A prime equals J Z naught tangent of beta D. All right. And let's assume that D here, D is a lambda over 8. Okay. So since we have D equals lambda over 8, then Z sub S over A prime is equal to J Z naught. And then we have tangent 2 pi over lambda. And then times lambda over 8 J Z naught tangent of, that's 4, pi over 4. okay, which is J Z naught. How much is tangent pi over 4? It's sine, excuse me. How much is that? Oops. These are the cosines. These are the sines. This is pi over 4.
1, correct?
Yes, 0, pi over 2, and then so on. That's pi, 3 pi over 2, and so forth. So this is sine, this is cosine, so it's 1. So we have that ZS A prime is 1 times J Z naught. So it gives us this. All right. Now, we have, from there, we have to find y S A prime, which in fact is 1 over Z sub S A prime, which is 1 over J Z naught, which is, let me see, how much did we, okay, which is minus J 1 over Z naught. And now let us assume that Z naught, how much did I say was Z naught? We did not say. Let's assume that Z naught is 50 ohms. Okay, so this is going to give me YS A prime is minus J 1 over 50, and that is going to be in Siemens. So it's going to be minus J 0.02 Siemens, right? So now we have Y sub in at AA prime to be this one. And we were trying to calculate this. Okay, and then we have this one. So now the total admittance at AA prime is the sum of the two admittances. So let's see what we get. So now step 3, we have that Y input at AA prime is equal to Y, how much do we call this one? We called it the same. Okay, let's see. Sorry for all of this. Y input, don't call it, and oops. Okay, so here.
You stop screen sharing when you got the call, ma'am.
Oh, thank you. Okay. 1 second. It stopped sharing. And it stopped also maybe this one. Wait, let me see. This one I am. Here. That's recording, so share. Yeah. Oh, wait. That's kind of weird. I know what it is, so join meeting. That's not where I want to go here. One second, excuse me, let me go back to this. And go connect my. Okay, 1 second. Okay.
Recording in progress.
That's okay. Screen. Okay. Okay, now you see that. Perfect. So now we have to equal. What did we say? The other one was 0.01. And then this one was minus j 0.02. And that's what is Siemens. Or if you want to find from here, the input is 1 over y input, which is 0.01 minus j 0.02. And that will be in ohms. And then what do? We multiply with the complex conjugate of the denominator. And that is going to give 10 to minus 2 and 10 to minus 4 plus 2, 4 times 10 to minus 4. Okay, which then this is going to give 10 to the 4 divided by 5. And that's going to be 100 plus j 200 divided by 5, which is going to be 20 plus j 440. And that is in ohms. So practically we have the j z input impedance is going to be 20 plus j 40 ohms. Okay, any questions about this? So these are two pieces that you will need to solve the problems that I gave you for problem 1. Let me see, since we are here, let's see the problems. Okay, so assignments. Take some time to load it, to bring it up. Why though? It's kind of strange. Assignments, homework. Other, I don't know. Okay, so what you see here is that you have similar to the combination of the two problems I gave you for the first one, but I am asking you to find D. So D is not known and Z01 is not known. So you will have to follow exactly the same process that I did, but you're not going to be able to know exactly how the two impedances are, like the green and the purple one, if you remember. And then you will have to just sum it up until the end and then equate the admittances to 20 millisiemens. And then from there, you're going to be able to find D and Z01. And even if you're going to have one equation, you're going to have two unknowns, one from the real part of because a complex is going to be a complex equation, one from the real part and one from the imaginary. So I will do a similar problem to this, to the design problem, but for something different to be able to see how I would manage that. And then it's circuit B. Now in the difference, the second one is using the Smith chart. So what I will do next, I will do a different problem with unknowns. So like a design kind of problem. And then I will do it first analytically and then with the Smith chart. But what I wanted to tell you is that the fundamentals on how to deal with a quarter wavelength line and then a stub that is short, it is like short at the end. I gave them to you as a problem, but I found the total input impedance because practically I knew everything in that problem that I gave you. All right, I had given you the characteristic impedances and I had given you also the distance D. Now, you don't have D and you don't have Z01, you have Z02, which is 50 ohms, but you don't have Z01. But I give you the input admittance. So it's kind of a reverse problem. It's the same kind of approach you will see, but at the end, you will see that you have to do one more step. So I'll give you a different problem for that. And then we're going to use the Smith chart for that different problem. Any questions so far before I give you a problem where some of the dimensions are not known? Okay. So I don't hear any comments. So then we can leave this one and go there. All right, so now this is problem 2. This is problem. So let me, in fact, be able to. Let's do that capital. And then do this capital. Okay. So let's solve another problem. See. Okay, in this problem, I will give you the following. I'll give you a transmission line. And then let's assume that this is Z0, Z0, 1. Let's assume at the end, as a resistor. Which is 100 ohms. All right. And let's assume in this case, no, leave it that. Let's assume that this L equal L equal 3 or 3 quarters of a wavelength. Okay. And then let's assume that I have here an impedance Z, which I do not know. And then I'm asking you to find. So then, and here I want to have Z input to be 50, to be 30 minus J 50 ohms. That's what I want. Okay, so find Z01 and Z so that in fact, I'll make it a little more complex, closer to what you're gonna do. So let's assume that instead of Z here, you have a stub. Okay, which is open. In fact, normally I will write it. Let me do it a little better. I don't know, like the design here looks horrible here. So okay, this is a series stub, but is okay, better. I'm gonna do this. Okay, so series, maybe let's do it like that. Series stub, but it's open at the end. Okay, and that has 50 ohms here. And this one is D. Okay, but it's a series stub. And then we want to find Z0 and D. So that Z input is given, all right, as above. 30 minus J50 ohms. All right, so first step 1, solution. Step 1. We want to find the input impedance here. Z, let me call that A, sorry. This is A prime. This is B prime, okay? So step one, find Z input. Let me also. Okay, find Z input at BB prime. So this is gonna be all right, and then let's try to find this input impedance at AB. All right, so now we have step one, find Z input at BB prime. And therefore, what we have as before is that Z input at BB prime equals Z01, all right, which we don't know. And then is RL plus J, Z01 tangent of beta L, and then Z01 plus J RL tangent beta L. Okay, how much is beta L? Beta L is 2 pi over lambda times distance is 3/4 of a lambda. Therefore, this one goes, this one goes, and therefore this is 3 pi over 2. Okay, and then we have tangent of 3 pi over 2 is sine of 3 pi over 2 divided by cosine. And how much is that? Minus 1 over 0, minus infinity. Okay. Because of that, as before, as we discussed in our previous example, we have that R J Z naught 1 of tangent beta L is much larger than RL. And then we have the J RL tangent of beta L is much larger than Z01, which means that I can eliminate this and that, and then equation 1 gives us that Z input at BB prime is going to be J Z01 squared divided by J RL, and therefore we have that Z input at BB prime is Z01 squared over RL. Okay, that is one equation. That's equation 2. Okay, so now we found the green one. So let's put it here so we remember it. Okay, let's now try to find Z input at AB, which is the input to the stub. All right, so the stub is open. So now step 2. Find Z input at AB. Because the stub is, well, we will write the same exactly equation, which is the stub is open-end. So Z sub L is infinity. I mean, the load is infinity plus, let me in fact, if you don't remember exactly, so it's going to be Z, it's 50 ohms rather, which is 50. And then you have the load, which is infinity, plus J. Let's put, in fact, the load of the stub. Okay, the load of the stub would have been, let's call it RS is infinity. All right, because it's open circuit. Okay, so in this case, it would give us RS plus J50 tangent beta D over 50 plus J RS tangent beta D. But because RS is infinite large, then I can make that go to 0, I can ignore these terms. All right, so practically, I can have that Z input at AB will be 50. And then I will have RS in the numerator and J RS tangent beta D in the denominator. And this I can cancel. So practically, Z input at AB is going to be minus J50 cotangent beta D. Okay, and that is this impedance. All right, so now let's see what we're gonna do. We're gonna sum the two impedances. All right, let's go back. In fact, here, 1 second. Let me take this smaller. Okay, so now let's go back here. The total impedance is the sum of the purple Z input at AB plus the green Z input at BB prime. So step 3, we know Z input is the sum of Z input at AB plus Z input at BB prime. All right, so now what we have is the input is minus J50 cotangent of beta D plus Z01 square over R sub L. And how much is R sub L? 100. Divided by 100. Okay, I have that. Now, how much is the input? The input is 20 plus J40. So I want from here to make 20 plus J40 to be equal to minus J50 cotangent beta D plus this one, Okay, so now you have two complex numbers. So the real number, the real parts have to be equal, and the imaginary parts have to be equal, which means 20 has to be equal to Z01 squared over 100, and 40 has to be equal to minus 50 cotangent. Oops. Okay. And from the first one, we find that Z01 has to be the square root of 20 times 100. And from the second, we find that B has to be the inverse, so D, beta D rather, has to be the inverse cotangent of minus 40 over 50, 4/5, okay? And, or cotangent inverse minus 0.8. Okay. All right. So let's use a calculator. Let's see. So what do we have? The first one, Z01 has to be the square root of 20 times 100 square root. Wrong. No, that's okay. 22,000. No, made a mistake somewhere. So 44. So Z01, this is 3. And this is 4. So from 3, we find that Z01 is 44.7 ohms. And from 4, let's see. So inverse tangent of that. And therefore, and 1 over x. So from here, we find that beta D is, it's not in radians. Not exactly. So let me see, how much is cotangent of minus 0.8? Let's try to do this again. In degrees. From the beginning. 0.8 inverse tangent. Now 51. No, wrong. I'm going to do this again. 0.8. Yes. What is it? much it is. Did you guys find it? Okay. It's minus is 51.34 minus 51.34 means 51.34 minus plus 51.34 minus 51.34. 128. Let me see. Tangent inverse. Okay, it's 128. 8 in degrees from 4. Since beta is 2 pi over lambda, that means 360 over lambda times d equals 128, which then means d over lambda equals 128 divided by 360, which is 0.35, which means from here that d has to be 0.35 lambda. And that's how we found the solution. Now we are going to try to find the same solution using the Smith chart. But do you have any questions so far? Okay, we are going to try to find